The title, people may be wondering what about the first three words that came there. So I like to start that out with explaining where that came from. There we go. So that comes from a poem by who I consider the original poet laureate of the North, Robert Service. And it's from the Ballad of the Northern Lights. And if you'll indulge me, I'll try to read this here. They danced and they danced like the devils dance over the naked snow. And soft they rolled like the tide upshoaled with a ceaseless ebb and flow. They rippled green with a wondrous sheen. They fluttered out like a fan. They spread with a blaze of rose-pink rays, never yet seen by man. So that's a really nice introduction to Aurora. And in fact, I can imagine if I'd never seen the Aurora, those words would probably give me at least a sense of what you might expect to see the Aurora. Now, actually, who here has not actually seen the Aurora before? That's what I thought. That's good. So we can sort of dispense with the idea that nobody has seen it before. So that's a very evocative words. But is that really an accurate description of the Aurora? Well, it's accurate in that it evokes what we think it is. And it certainly conveys the excitement and the pleasure of watching the Aurora. And that's certainly been around for a long time. But you know, as technology has advanced and we try to actually quantify what's going on with the Aurora, it's been fun to watch how that technology has advanced and how our understanding has advanced. So here I'm showing over a century of observations of the Aurora. This is a couple of Norwegians, Karl Stormer and Birkeland, in 1910, making observations of the Aurora. This is some of the first work to determine the altitude of the Aurora. And you can see back there, and obviously the way to do it was with lots of furs on, and using a film photograph. Those are plate glasses. They took tens of thousands of plate glasses from two sites, and using triangulation, they were able to determine the altitude of the Aurora, and they were quite accurate. It was pretty amazing for that technology. And then we work up to today. Here's a state-of-the-art imager I'll talk about a little bit later. And here's the kind of hardship I have to go through sitting in my office at Poker Flat. And I'm not wearing as much fur as they are, but it's nice and warm there. And then, so the description of what we can do with all that data, you know, here in the Middle Ages, that's what they could do. They could draw pictures trying to figure out what was going on. And their ideas were candles or ice crystals in the air. And now we can do amazing things with the digital revolution, computational power, visualization. We can do amazing things with that. Now, that's all great. And we still got to ask the question, just because we do that doesn't mean we understand it any better. So basically, advancement of technology, they can enable improved understanding, but not necessarily so. So one of my goals tonight is to make sure that anything I show you is showing you advancements and not just replaying. I don't know how many times I've gone out and made a measurement, and then I'm about to think about publishing, and I go off and look, and somebody's already done it. Somebody back 30 years ago. So a lot of things have been done already, so I want to make sure we're moving ahead. Now, here's a little bit of an outline for the talk. So I want to make sure everybody's on board here. I'm going to do like a 101 of Aurora in about 10 minutes. Now that's going to be a little hard, but I want to make sure everybody's sort of on the same page, at least as far as what we're talking about as far as the measurements. Now I'm a bit of a gearhead, so I'm probably going to talk about the technology, the cameras, too much, and not enough about the science. So we'll try to get through that quickly. But I'm going to talk to you a little bit about what we're doing now and how that is different from what was done even 20 or 30 years ago, let alone 100 years ago. And I'll try to talk about the science discoveries that have come out of this amazing advance in the digital technology we see now. So, and I'm going to give you a few words here. Again, for these lectures, I always have to remind myself I'm not sitting at the GI, and if I say some of these words, not everybody knows what they mean. So here are a few things. Photon. Now, for a long time, people thought that light was an electromagnetic wave, and that's true, but it also comes in individual packets. And so we call a photon one of those individual packets. And you can actually go off and measure a single photon. So it's undividable quantum of light. By the way, its energy is inversely proportional to its wavelength. The wavelength is the color you see. Quantum efficiency, I'll talk about that a little bit later on, but basically it's how well a detector measures the light coming into it. We'll talk about that. You'll see a lot of places we're going to put a capital R or a KR. That actually stands for a Rayleigh. That's named after Lord Rayleigh, English physicist from 19th century, I think. Anyway, that's the unit of optical brightness. So a bigger number just means it's a brighter aurora. You don't need to know what it really means. And the last thing is a kilogram. It's a kind of a funny thing that we use a lot. The aurora is actually a 5-dimensional problem. You've got 3 spatial dimensions, you got things there, you got time moving around, and you also have wavelength you got to worry about, the color of the aurora. And I can only display maybe 2.5 dimensions on a screen like this. So we have to make compromises. So one thing we do is what's called a keyogram. So we take a series of images like that, and we take a stripe down the middle, and we just lay it out vertically like that over time. And this is what that looks like. So this is the red part of this image down here, and you can see here about 950. Sure enough, there's a little bright red spot there, and you can see that red spot there. So what you can do is you can tell where in the sky, south to north, the aurora was brightest as you went along. So there'll be a lot of places where I show different kinds of keyograms, and that's what I mean with a keyogram. It's basically just slice the sky and lay it out in time. They used to do this mechanically. They'd actually have a film camera moving along with a slit, and they would just expose it for a little bit of time, move it over, and expose the next time. But we can do that digitally now. Okay, so what causes the light in the aurora? Well, what happens is electrons, those things that spin around the outside of the atoms, they're accelerated somewhere out deeper in space. It's what's called the magnetosphere. We don't need to worry about that right now. They get accelerated to high speeds, and I mean like tens of thousands of kilometers per second, very fast. They come down, and they have to follow magnetic field lines, but they come down toward our atmosphere, and as the atmosphere gets thicker and thicker, we get towards the surface. There are more of these atoms and molecules in the way, and they bump into those. When they bump into those, they lose a little bit of energy, and through a process we'll talk about in a second, what comes out is a photon, a little bit of light. So what we're seeing is the result of electrons bumping into our atmosphere. Now this is the same thing that happens in a neon sign. Now I don't know if everybody's, well, I don't know if physicists maybe spend too much time in bars, but we've been in a lot of bars and seen neon signs. It's the same sort of thing there. Hopefully you don't do that. This also happens between about 100 kilometers and 300 kilometers altitude. That's about 60 to 180 miles. So when you're watching an aurora, the bottom of that aurora is about 60 miles high. So it's a long way above those clouds. Let's see, I can do that. The other interesting thing is, and back in the 19th century, people started doing this. They started taking a lot of spectra of different things, and one thing they did is took a spectrum of the aurora. So if you take some white light, like from the sun, and you bend it through a prism, what you usually get from the sun, you get a rainbow, right? You know, that's what happens with the raindrops in the air. If you take the same, or if you take light from an aurora, you bend it through that same prism, instead of getting this nice sort of smooth transition from color to color, well, you get a whole bunch of individual colors that come out, and sort of gaps in between. So it's kind of interesting. It took a while for them to try to explain that. So why is that the case? Well, if you go back to grade school and talk about how atoms and molecules are made up, right? So the nucleus in the center, and these electrons are orbiting around there. Now I put circular orbits here. It's not really circular orbits, but this is a good schematic. And what happens when an electron comes down, a high energy electron comes along here, bumps into that atom, and the first thing it sees is the electron. It gives that electron a little bit of energy, so it can go from that low energy orbit to a little bit higher energy orbit. So it goes from here, it bumps up to this guy up here. So that's the excitation process. But everything likes to be at the lowest level. You know, you put a marble on a hillside, it wants to roll to the bottom. The same thing happens in the atom. So it wants to go back to its lowest energy state. So it does that, but it has to lose some energy. You can't create energy out of nothing. So when it does that, out comes a little bit of light. And because these orbits are very well defined in energy, when that transition happens, the energy that that photon has is very specific. And because that energy is very specific, the wavelength is very specific, and that's what makes up all those individual lines in the spectrum. Well, this is great because we can actually use this to discern both what species are being excited up there, and it also helps us determine how energetic those particles really are. So I'll give you some hints here, and you can go amaze your friends with saying, oh, well, that's obviously oxygen aurora. So if you see the really deep red up at the top, very high altitude stuff, that's atomic oxygen. Now the oxygen we have right here is mostly molecular oxygen. This is atomic oxygen. It gets split at high altitudes. The green line, and that's what most people see, is a lot of green. That's also atomic oxygen. It's just different sets of states. When you get really good aurora, you see this nice pink lower border like that. That pink lower border is a combination of some red, neutral molecular nitrogen and some sort of blue-violet ionized molecular nitrogen. And that's a sign. When you see those pink lower borders, that's a sign that those electrons are very energetic, or they're coming down deep into the atmosphere where the nitrogen is starting to be more dense than the oxygen is. So you already know a lot of stuff now, right? So if you go and see red aurora, you know it's very low energy electrons coming in. If you see green aurora, that's a good standard one. If you see that pink lower border, those are really energetic electrons. That's all we do. So you guys can be rocket scientists now. Now it turns out if you use the ratios of these, so if you take the ratio of that green and that pink on the bottom, you can actually come up with a diagnostic for how energetic those electrons are. So that's one of the things we do, and I'll talk about that a bit more. I already talked about this, but how high are they? And this gives you an idea of how high they are compared to other things. So here's, as well as I can do in PowerPoint, here's a scale model of the Earth, and here's more or less where the auroras are, right? So Earth is a big place, so that's a long way up, and here's that blown up a bit. Now if we take that 100 kilometers, that's basically the bottom of those arcs. You can see what we can do here. The ozone layer is about 30 kilometers up. Airplanes go to 15 kilometers. Tallest mountain's just under 9 kilometers. Research balloons go up to 50 kilometers. There's some things called noctilucent clouds that are up at 80 kilometers and such like that. So gives you an idea. Auroras are a long way up there. I know they seem kind of close sometimes when they're really active, but believe me, they're basically 2/3 of the way from here to Delta Junction. If you laid them down, or if you drove straight up, it'd take as long. So, and how do we know that now? Well, like I said, Stormer would go out in his fur suit and take pictures from 2 places and figure out they're that high. Now we can just put a camera on a space station and take pictures of it as it goes by. And you can see here's the limb of the Earth out here. That's the edge of the Earth. And you can see the auroras are definitely well above that. And if you measured that, if you could scale it, you would see that those are probably, the peaks of those arcs are probably at 110 kilometers, something like that. Now this kind of points to what I'm going to start talking about now, is just how amazing the technology is now to do this. The first images from, anybody remember Skylab before the space station? The first images from Skylab, the astronauts came up to Alaska to the Geophysical Institute and were trained by a fellow there named Tom Hallinan to take those pictures. So we were involved with some of the first images of Aurora from the space station that way. You can go to some NASA sites and get lots of these. I've got a couple of more I think I'm going to show at some point. And one more thing about auroras, people think there are lots of different forms, and that is true, but the way the aurora looks also depends on where you are when you see it. And here's a little bit of a schematic. So here I've got an auroral arc. One thing about these arcs is they do move up and down, or they are lined along magnetic field lines. And those are tilted a little bit here. They're more or less straight up and down because we're so far north. But if I've got a camera here and I'm looking at that arc, it turns out that arc's actually quite thin. In fact, there are cases where we've measured arcs, at least subarcs, as narrow as about 100 meters. Most arcs are about 2 to 4 kilometers wide, something like that. But if I move a camera over here, or I happen to be here when I'm looking at the aurora, now it looks like a drapery. That's just the difference between, sometimes you see the arcs on the horizon, you see them as draperies, but you get this thing called the corona aurora, and it looks a lot different. You can see how thin things are. Okay, so we've learned a little bit of the aurora. Let's think about how we want to image the aurora. So we've got individual emission lines. So it turns out if we use some narrowband filters to image it, that might tell us, especially if we want to do things like look at the ratios of the emission lines. So we want to use filters. I showed some pictures earlier on. You can see they're highly dynamic, and we know that from watching them. When they're really bright, they're moving really fast. So we probably want, and that's both in motion, how they move, and also intensity. Sometimes they're very dim, sometimes they're very bright. So we probably want to use high frame rates. We want to take movies at high frame rates. There's also, there's also a large range of intensities. So we want a camera with large dynamic range. We want lots of levels to be able to measure that. Another thing we know, or I will tell you, is that we're also usually photon starved. Meaning, even in this room right here, we've got a lot of light coming around. When you go outside to watch the aurora, unless it's a really bright aurora, there's not much light coming out of that. So what we really need is a lot of high sensitivity cameras. And I'm going to tell you how that has improved over the years. So I had this whole plan about telling the whole history of imaging aurora, but I think I'm going to shorten that quite a bit because we need to move on to talk about the science of aurora. But the interesting thing I thought about as I was talking about the imaging technology is that's actually it's just the opposite of what happens in the aurora itself. So remember back to the aurora here, you've got electrons that come down, they bump into something, and it creates a photon. Well, now I've got a photon I got to deal with. I got to collect that somehow. Well, the way I do that is that photon comes down, it bumps into something and turns into an electron. And because I've got electronics, not photonics, but electronics, I can now do something with that photoelectron to be able to measure it. So, like I said before, a key parameter in the imaging is the efficiency of how this conversion medium that turns that photon into an electron, how efficient that is. And that's called the quantum efficiency. And basically all it is this: if you've got 100 incident photons coming in, if you've only got 10 electrons coming out, then your quantum efficiency is 0.1, you only get 10% of them. Now for imaging the aurora, that's not what we want. If we've got 100 incident photons coming in and we get 100 electrons coming out, that's good. We're measuring every single photon as it comes in. So what we want is a quantum efficiency that's very high. And the closer we can get to 1, the better. All right? So here's sort of a time history of what we've been able to do. Obviously, the first thing we did was our eye, and our eye has a quantum efficiency I can't remember offhand, but it's actually quite amazingly good, but it's still on the order of about 10%. Photographic emulsion, quantum efficiency about 10%. About 1 out of every 10 photons that comes in actually gets converted to something that you can see on the photograph. The next, and photographic emulsion started in the 1880s. I mean, well, actually it was 1860s, because in the Civil War, there were photographs back then. Electron tubes came along later in the 1940s, 1950s. Quantum efficiency of those guys was about 20 to 30%. This is what's called an image orthicon. I was going to show more pictures of data taken with that. Some people in this room spend a lot of time working with image orthicons. It was always quite a treat when the graduate students finally got to be able to touch the image orthicon. The control panel for that thing looked like a nuclear, control panel for a nuclear power station. There are knobs all over the place. Each of these little individual things back here had a knob for it. So it was quite a treat when we were able to finally to be able to touch that and run it. Then we went on to image intensifiers. Again, they're kind of 20 to 30%. By the time you actually get to CCDs, and image intensifiers came around in the 1960s. CCDs came, some of the early CCDs were in the late 70s, but the real ones people started using were in the 1980s. Now we've jumped up to about half. So now we're getting about half of the photons coming in are turning into electrons that we can use. CMOS, this is sort of out of sequence. Those are the newest ones. And they've sort of taken a step back, but there's some advantages there. But really, the gold standard now, if we use a CCD and you process it in a certain way that you basically put it together, turn it over, and then basically take off part of the back, it turns out to be very, very efficient then. We're getting quantum efficiencies now of 90%. That's about the best you can do, right? If you got 1 or 100%, that's it. So this is really the thing that's changed a lot, is we've changed our sensitivity about a factor of 3 to 4 in about a 20-year period. So here's what a state-of-the-art camera looks like. I won't belabor it. So lens up front to image. Here's a filter cell. Like I said, we want to filter things. We want to be able to look at individual lines if we need to. Some relay optics back here, and here's this camera right here. This is about a $100,000 camera, because these cameras, right, the processing for those chips is very expensive. So this is going to be a little experiment here. So here's an old intensified CCD. So this basically went to a video recorder of some sort. And here's one of the new cameras here. What I'm going to try to do is catch it as it goes by. I've done nothing to these two things, but what you can see is the contrast in this is just a lot better. You've got more dynamic range. You've got a lot better resolution in the whole thing. But it really is a really amazing advance. Now, I didn't talk about the optics themselves, the glass that runs the camera, that focuses stuff. That really hasn't changed much. I mean, the glass has done a pretty good job. The other thing that's really amazing now is obviously everybody knows about computational power. In the 1980s, we had TRS-80s and early IBMs. Now my cell phone has more power than any of those computers did back then. So the ability to do the analysis of all these digital images is all really pulled along too, as well as the speed to be able to collect all the data at the same time. Okay, so I'm just going to run through a sort of a vignette of several things that we've been doing the last, I'd say, about 10 years now, and try to talk about how this advance in technology has helped us do this. Now, one thing that is very key to people who work in the Aurora is what's called the Auroral Substorm. Now, the Auroral Substorm, for us who like to go out and watch the Aurora, that's when the Aurora is really dancing around, very active. That happens nominally about every 2 hours when the conditions are right. But the reason that happens is not well known. That's one thing we're still working on. We've sent many missions up there to try to figure this out. It still eludes us for several reasons. This last year, Toshi Nishimura at UCLA has made great strides using a couple of cameras that we've been running here at Poker Flat. Basically what he's showing here is, here's where the substorm happens. That's when the aurora really brightens up and you see all that activity. What he's curious about is what's the activity going on beforehand. And what he sees, here's a keogram, but we really call it an east-westogram. Instead of looking north-south, we're looking east-west. And with that, we can see these waves sort of rolling in. And what he's been able to find is he's got some wave structure that's nobody's really ever been seen before because the cameras have not been sensitive enough. And he's able to now correlate that wave structure to when that substorm happens, when the brightness happens. And that's going to tell us a lot more about what's happening about in the magnetosphere where these substorms are being formed. So basically this filtered low light level capability was the reason we could do this. With the old technology, it was going to be too hard just because the low light level imaging ability down here was going to be very hard. So here are the images that went along with that, and we've mapped those out. This guy right here, I'll come back to. We've got a radar out at Poker Flat right now, too, that also gives us the density of the electrons at high altitudes. I'll talk about that in a bit more. Here's a different example. Get this started. This is a different night, but it gives you an idea. Again, this talks about the dynamic range of these cameras. So here it is. In just a second, you'll see up here, this guy will bead up and it'll get very bright. Here it goes. And then this is what we call a substorm. What happens is, that's north. These arcs go to the south and they brighten and everything moves to the north and it gets very active. Now this is a time lapse. You can see the time going by there. This is sped up about 30 times. You can see how this camera was able to handle that large dynamic range. We had that very dim aurora beforehand, and then we could see that real bright aurora later on. Let's talk about spatial scales. With these new cameras, if you put on a very narrow lens, you can zoom right into very small scales. Here's a scale, again, at 100 kilometers altitude. Here's a scale of what each of these pixels has, or that's the scale of those images. So we'll be able to see things down to a few tens of meters across. This is a filtered image, and it's taking images at 20 seconds. Again, we're looking at these structures moving across here, which are indicating some sort of plasma wave out in the magnetosphere that's forming them. And based on that, we can work with the theoreticians to understand what that plasma wave is, and therefore what's causing this sort of structure there. And again, what's the source of the aurora that happens here. So that's very fine spatial scale. Again, that's down to tens of meters across. So, you know, kind of the size of this room. But you got to remember that the aurora is about 4 kilometers across. So that's from here to the river or something like that. So pretty fine scale. Now, the opposite, what if you want to look at really, really large areas with pretty good resolution as well? Well, how do you do that? You use an array of cameras. So there's a NASA mission called Themis. Don't ask me what the acronym is because I can't remember anymore. But they decided to put in about 20 different all-sky cameras across Canada and Alaska. And now instead of going for the really fancy, expensive cameras, they ended up going with actually fairly cheap cameras. And that's the amazing thing now is with the explosion in consumer products, you can buy a little camera like this, which is what amateur astronomers use, for less than $2,000. Something like about $1,500 or so. A couple of lenses on front, some electronics underneath it, and off you go. So they put in these 20 across here. These circles are basically showing you an all-sky camera field of view at about 100 kilometers where the aurora happens. And then if you put all those together and you get good luck with the clear skies at all those stations and all the cameras are working, here's what you get. So this is time here. You can see as this moves across, this is where the terminator, that's where the sun has gone down. This is a good night, not a lot of activity, and you can see all those cameras are picking up substorms, a whole bunch of different fields of view, and you can see how extensive the aurora is when it's this active, and how activity over here may not be well correlated with that activity over there. And you also see north to south, you see pulsating aurora down here, where you see active arcs up here. This has been a wealth of information for people in the auroral community. Lots of really good information has come out of this. Because at the same time, we've got 5 satellites flying around in the magnetosphere, measuring the particles, the electric fields, other parameters out in space that match those. So this is repeating it again. We'll watch it one more time. Yeah, so there's sort of a first substorm that kind of settles down. You watch here again, there will be another substorm a little later on that happens in that place again. There we go, a little bit more there. But it gives you an idea of how extensive Aurora is. It happens everywhere. It happens all across the auroral zone. And when it's really active, it's really active. So we've gone from fine scale, a few tens of kilometers, to thousands, tens of thousands of kilometers across. And these all have about 2-kilometer resolution, so that's quite a number of elements to look at. And again, this is enabled by low-cost cameras in this case, and a lot of computing power, and a lot of networking power. High frame rates. This is not particularly high frame rate, but this sort of drove a measurement we wanted to do. I keep forgetting to mention this. Actually, this is these are the PIs of the rocket that's on the rail out of Poker right now. So they've been out of Poker for quite a while. But this is another one of those kiograms. This is, again, north-south. In this case, it's not an all-sky camera. It's a narrow-field camera. And here's a distance along here. So it's, it's about 1 kilometer resolution. And what they do is they're looking at this pulsation patch, and it does what you're supposed to do. It lasts for about 5 to 10 seconds with a period of about 10, 15 seconds like that. But what's interesting is look at this right here. So here's this big pulse right here, but here's some sort of fuzzy stuff there. We wonder what was going on. So another colleague from Japan came out with a TV team from Japan and brought a camera that can run at 800 frames per second. So now we're really subsampling what we've been able to do before. So here's this patch that here's a pulsating patch that we're looking at before. A little more active than you would think. But watch over here. There's some little patches here that just kind of flash on for just a single frame. What looks like a single frame. So when we take that, and now we do our keogram thing. That's why I wanted to introduce keograms, because we use keograms all the time. We take that keogram, and we take this region right here, and we kind of spread it out. Now time is going this way. This is the first time, this is the last time. And so here's that bright patch you saw over here coming on and off. Here's the second bright patch. Here's a little place where it gets dark afterward, which is kind of interesting as well. But what we're going to do is also take now just a time history along these guys right here, because look at these guys right here. Little short bursts. So if we take that, here's this one. This is this plot right here. So if you take that plot right there, it gets bright, gets dim, gets bright again. Here's this plot over here. It doesn't get bright and dim like that, but you see these little bumps. We expand that up to here's 1 second, and we look at one of these guys right here. That's 30 milliseconds. Now that may not mean a lot to you, but it turns out for forming pulsating aurora, that can almost not happen. So it turns out pulsating aurora is supposed to happen when these particles, which kind of get trapped on bent field lines like this, if you get enough particles in there, they just kind of sit around, they bounce back and forth from essentially hemisphere to hemisphere. It has to do with electrodynamics of that shape field line. The only way you can get a particle that will bump down here into our atmosphere is if you kind of kick it somehow. If you give it just a little bit different orientation, it'll come down and bump in there. And so the idea was there are these waves that happen that will kick them into that loss cone, we call it. Well, if that happens out here, it turns out unless that particle, or all those particles have the same energy, they have different energy, they all have different speeds, so they're all going to end up down here at different times. And when you do that calculation, which we've done, that should take about 800 millisecond pulse instead of a 30 millisecond pulse. So what that means is at least one of these things true. Either these trapped particles out here must be cold, they must not have a dispersion of energies. The scattering mechanism must select a single energy range, or the scattering mechanism happens a lot closer than we thought. Because if it happens right here, that dispersion is not going to spread it out as much. So this has really thrown kind of a wrench in our idea of what's going on with pulsating aurora. So I've got a grad student working on that right now. And here, that also kind of leads to the whole idea of, we call all of these things pulsating aurora. Again, these are all sky images of pulsating aurora. So we call all of these things pulsating aurora. But the more you look at them, they certainly look a lot different from each other, don't they? They all have sort of the basic idea, but there's a lot of differences in there. So you can well ask, is the same mechanism happening in all these cases? And that's kind of what one of the things we're probing now. Pulsating aurora has kind of been the stepchild of aurora. People come out, and they come out for that big substorm. It gets really exciting. Off it goes. And then they say, okay, well, the substorm's over, and they get in their car and they drive home. And the pulsating aurora is the stuff that happens after the substorm. So the pulsating aurora was not studied as much as the substorms were. So we're kind of catching up on that now. Another thing is pulsating aurora also is usually pretty green. Remember what green and blue mean? Green and blue mean high energy particles. Until I started running the camera at a poker flat with multiple filters, you'd see pulsating aurora going along, and you think, oh, that's fine, there's pulsating aurora. But I started doing that, and I started seeing these funny little red blobs. You can see all these patches are moving across here. They move across there for reasons I won't go into. If you watch this red patch, it actually is moving the opposite direction. So here's another little bit of a mystery. We've got a different kind of precipitation going on, electron precipitation going on in the middle of this pulsating aurora patch. So applying these new techniques, low light level techniques, we're finding new and interesting things. And I'd like to give you answers, but it's actually bringing up more questions than we can answer right now. Now, optics themselves are not going to answer all these questions as well. We use a lot of things. We use rockets, we use satellites. We also use some of the other assets we have here at Poker Flat, and that's this incoherent scatter radar. It's called AMISR. It's called the Advanced Modular Incoherent Scatter Radar, or we also call it PFISR, Pfizer, or P-Pfizer, some people call it. And what it does is it sends out a pulse, and based on the return pulse it gets from the ionosphere, you can tell how many electrons are in that volume of space, whether they're moving, and what their temperature is. So it's quite a versatile instrument. And it's also for those of you who know about radar, it's a phased array. So instead of having to steer a big antenna around in order to trace out different places, it can actually do multiple beams at the same time in different directions. So we can essentially image the ionosphere while we're doing image the ionosphere by radar while we're doing imaging by cameras. So what you'll see when this rolls around again is as one of these arcs moves through here, these guys light up, which means the density, the electron density in that region, because of ionization due to the electron precipitation, has gone up, and we get more electrons and ions in that region. It turns out you can use the GPS radio signals as another diagnostic for what happens in the ionosphere as well. Because you've got a radio signal having to go through the ionosphere to get to the ground, and because there are two frequencies that GPS sends out, if you look at the differences in those frequencies and some of the details of the waveform, you can actually distinguish things that happen in the ionosphere. So what I'm showing here is each of those is what's called the pierce point. It's the position in the ionosphere from which the ground observer to the satellite happens. So you got a line between those two, and it goes through 110 kilometers. So each of those is what's called the pierce point. It's where it happens to go through the ionosphere. The numbers there just indicate what the number of the satellite is, and the colors are just the colors. But the size of this cross indicates what's called the phase scintillation. It's how much the phase is shifted from where it should be. And this is actually one cycle, so when it goes bigger than that, it actually means the phase of that wave coming into the ground has moved more than one cycle. Now that affects our ability to navigate. If you move more than a single phase on a GPS receiver, it may have trouble locking, it may have trouble knowing where it is. So it's been an ongoing question, how does Aurora affect navigation? And so it turns out this is some of the first time this has happened. I just sort of did this on a lark, and everybody's been very interested in this. So you can see this is a very busy night, 17th of March last year. You can see as soon as the arc goes across where that pierce point is, the phase scintillation goes way up. The disturbance in that radio wave from the GPS signal to the ground is highly affected, on the order of two or three cycles in that wave. This is also seen in the low latitude, but it's usually a high altitude disturbance. This seems to be more of a low altitude disturbance, about the same altitude as the aurora. So again, we're combining data here. We can combine the optics and the GPS and learn a lot about each. So this does two things. One, it tells us we can start figuring out if we've got Aurora like this, how much is it going to affect the GPS? But we also understand the scattering from the GPS, so we can also use that GPS disturbance to kind of understand what happened in the Aurora. How is that changing the ionosphere locally? Now, a colleague of mine up at the GI, Mark Condi, and I have had this ongoing war about who can put the most things on one set of images. Now, the next one, you'll see that Mark won hands down on this thing. But this is really illustrative of what we're doing now. I'm talking about optics, but you really need to combine all of these data sets together in order to make a real understanding. So what he's got an instrument that can measure the wavelength of a certain wavelength of a certain emission line. This happens to be that red emission line from high altitude, very precisely. He can measure it so precisely, he can measure a Doppler shift in that wavelength and tell you how fast that particle was moving when it emitted that light. So he can actually measure winds in those particles at 300 kilometers altitude. So what he's plotting here are those wind fields he measures with an all-sky camera and this instrument. He's also putting some radars on there as well. So I'll play it here. I'm not going to try to describe what's going on here. I just say he just won. I gave up the whole thing after this. So these orange arrows are the winds going by here. This is actually a radar measurement showing how the ions are moving. These winds are neutral winds, so it's neutral atomic oxygen. This is ions of any sort moving around. And then you also see these circles right here give the temperature of that oxygen at those altitudes. And in a minute you'll see the Aurora coming through. He's using my cameras to show where the Aurora is happening while all this stuff is happening as well. And what you'll see is when the Aurora happens here, the ions start to move in different directions, and that actually has enough energy to move the neutral winds around. So the neutral winds just want to move because of pressure and other things like that. And as soon as the ions move around, you see the ions are turned this way now, and the neutral wind had turned around in response to that. So not only are we trying to understand what causes the Aurora, we're also trying to understand how the Aurora affects our upper atmosphere as well. So he gets the prize. So, like I said, just a few vignettes of the things we're trying to do with this new technology, and lots of fun movies. So we've had amazing advances in the technology, but we got to make sure that we use that smartly. That we're not, like I said, just reinventing the wheel every time we do that. And I think some of the things I showed you, I think, really fall in that thing. And it really does take a combination of all these instruments together. So I like to do the optics, that's what I specialize in, but the radar guys, the rocket guys, the satellite guys, we've all got to get together and work together. And I think we've got a nice combination here at Poker Flat and Northern Alaska now. We have sort of an ionospheric laboratory, and we're trying to capitalize on that and do a lot more work on that. So with that, I think I will entertain questions, and thank you very much.